We are very close to finally gauging gravity now. And so the next step from our previous discussion is to covariantize the uh, the the matter fields, right? So we'll start with covariantizing the matter field. Uh, and so let's begin with an example, right? And I'll take an example of a scalar or a massive scalar field phi, and its transformation properties uh, under the uh, under the general Poincare group are determined by this thing, that phi prime of y prime is or it is equal to phi of y under under global Poincare transformation, right? Okay, so or under global Poincare group, right? So this transformation law can be readily promoted to the transformation law under GCT, which was general coordinate transformations, right? So I can just write it as phi prime of x prime is equal to phi of x. Now with this and our previous discussion, the invariant matter action will become, or it will read as this thing is equal to the integral d4x square root minus g 1 by 2 g mu nu, where this g is the determinant of this matrix G mu nu, right? And partial mu phi partial nu phi minus m square phi square, right? So this is actually a pretty familiar, it sort of is a familiar action, right? Now, if I take the variation with respect to g mu nu, right? So with respect to g mu nu, I vary this action, the matter action. What do I get? I will get something that looks like this. Let me write it down. This is delta S of matter with respect to g mu nu field is equal to, so all I'm doing is I'm just varying this action with respect to the field g mu nu. So taking its derivative with respect to g mu nu, I get 1 by 2 square root minus g. I'll get partial mu phi partial nu phi minus 1 by 2 g mu nu. I'll have, now I have to be careful with the indices, so I'll have rho sigma partial rho phi and partial sigma phi, right, minus m squared phi squared, right? So let's just close the final bracket as well. Now, if you recall the expression that I wrote in previous lectures for this energy momentum tensor TAB, it was equal to the partial derivative of the Lagrangian with respect to the partial derivative of the field phi and partial b phi, right? And then there is another term as well, which is eta AB times phi. So this is the definition of the energy momentum tensor. Now I can promote the Lorentz indices in this. So Lorentz indices are now promoted to world indices. Now, if you recall from previous discussion, the Lorentz indices are the ones we have with A, B, C, and the world indices are mu, nu, and so on. So this is one of the things that I'll do for this energy momentum tensor. And the second one is that because we are now talking more generally I'll replace eta mu nu with the new field that we have, and that is G mu nu. Right, so you can recall these where did I get this G mu nu, and it was in terms of eta mu nu. How did I replace this G mu nu from the previous lecture in this series, right? So, well, with with this definition and these two these two things, right, I have T mu nu is equal to 2 over under root minus G times the variation in the matter action with respect to the field G mu nu, right? And so this thing over here, this energy momentum tensor, is the first triumph or the first success that we have gotten to so far. Now, as expected from our gauge theory reasoning, the gauging of the space-time, or by gauging these space-time translations, we have indeed found this T mu nu, right? So that's what we were doing since previous lectures as well. So this T mu nu is indeed now the source of the gravitational force that is mediated by the field G mu nu, right? Now note that in deriving this equation that I have, this one, right, this long equation, I have used some relations basically, which I think I should list them down over here. So if you try to do it yourself, you can look up these relations over here to to aid you in deriving the expression. So this is the change in the this, if you have these two fields together multiplied, or the matrices of these two, and G mu nu and G nu rho, the change in this is simply equal to the change in this delta function, which is rho nu, and we know that this thing is equal to 0 all the time. Right, now another one is this one, that change in the field G mu nu is equal to minus G mu rho G nu sigma delta G rho sigma, right? And finally you have this change in this thing, square root of minus G with respect to G mu nu, where again this G is the determinant of the matrix or the field G mu nu, is equal to minus square root of minus G over 2 times G mu nu. Right, so these are just some of the relations, and these relations also further they follow from the follow from this relation that we have, that the change in the determinant of some matrix M is equal to the determinant of the matrix M plus the change in that matrix M minus the determinant of the matrix M itself, which is further equal to, in exponentials, it is equal to exponential trace of natural logarithm of M plus the change in the matrix, and we subtract this exponential of trace of logarithm of the matrix itself. And this thing, if you can simplify this even more if you want to, it should be, or it is, the trace of the M inverse change in the matrix M. Right. Now with all this, you can further use your Euler-Lagrange equations to derive the equation of motion for your field phi, right, for your scalar field phi. And if you do that, you can do it as an exercise, but you get this thing 1 over square root of minus G partial mu times the square root of negative g, g mu nu times partial of nu plus m square is equal to 0. Of course, there is a field phi over here, and this thing is equal to 0. And this is the equation of motion that you get. Now, the interesting part is that you can reduce this equation or this equation of motion to the Schrodinger's equation, and you can do that in the limit of non-relativistic, let me write it down here, that it reduces to Schrodinger's equation in limit of non-relativistic and if your field phi is a non-relativistic field, right? So you get back your Schrodinger wave equation. And of course, you also make another assumption of a weak gravity field, right? Weak gravity field. And we'll discuss, or I'll discuss this weak gravity field in further lectures, right? And in fact, I will show you that this equation in this box indeed reduces to Schrodinger's equation in these two cases, right? Okay, now let's move a bit further and let's talk about the gravity sector of our discussion. And so far I was talking about the matter sector, right? Now, if I have to give my field g mu nu, if I have to provide it, give it some dynamics, right? So if I have to make the field dynamical or allow the field to propagate, that's what we are going to talk about right now. So I'm going to start by considering an example with the vector field v mu of x, right? And we know that this vector field v mu of x actually transforms as v mu prime of x prime is equal to some transformation matrix j mu nu of x times the vector field v mu of x, right? Now, then, in analogy to the Yang-Mills theories, one introduces the covariant derivative d mu, right? And the transformation properties of this d mu under the GCT, so under GCT, d mu transforms as, if I have this vector field v mu with it, it will transform as d mu prime times this vector field v mu prime, or instead there should be different indices over here, right? So to keep things clear, and this thing is further equal to, we know from our previous discussion as well, this thing would turn out to be j inverse sigma mu times j nu rho d sigma and v rho, right? And we can write down our covariant derivative d mu times this v nu. We can generally write it down as a partial mu v nu plus these symbols, these you'll see that these are called your Levi-Civita connections, or your another name for that is the Christoffel symbols, right? So that's what they are, and we'll define them in a bit right now. So note that this equation, this one, is, or it will be valid as long as this thing is satisfied, that this connection transforms as mu nu is equal to j minus 1 mu prime mu times j inverse nu prime nu times j lambda prime lambda. A lot of index gymnastics, right? And you have this this connection lambda prime mu prime nu prime plus j inverse with more indices lambda prime sigma partial mu prime j this sigma, and you'll have nu prime, right? Perfect. Okay, so now you can view or think of this this gamma, this symbol, as an independent field as well, right? You can think of it as an independent field, but it turns out that it's much more straightforward to go ahead and express it in terms of your field that you already know, or that we have the g mu nu field, right? So the metric field. And we can do that in this way, that if I write this down, if I use the above equations, and I can write this mu nu, this crystal connection, as 1 by 2 g lambda sigma partial mu g nu sigma plus partial nu g sigma mu minus partial sigma g mu nu, right? And you can recall from, if you have taken a course on general relativity, that this is how this Christoffel symbol or the Levi-Civita connection is described in your general relativity as well, right? Okay, so well, the simplest way to derive this Levi-Civita connection is to implement what is called a metricity condition, right? So what that is that it says that the covariant derivative of this g mu nu vanishes. So this condition actually is necessary for the Einstein's equivalent principle to hold as well. So it's important that this condition is satisfied for the Einstein's equivalence principle to hold. And it also implies the vanishing of the connection in the absence of a gravitational force. And in such a case, you must be able to recover the original Poincare invariant theory, right? But anyway, proceeding as we would for the Yang-Mills theories, we will introduce a field strength tensor for the case of gravity, right? And I will use the vector field v mu as an example. So this would again be defined by the this commutator relation of the covariant derivatives times this v, let's take v beta, is equal to r beta mu nu alpha times v alpha, right? And we're getting somewhere now, because this gives us an expression for this thing over here, which is r beta mu nu alpha, and we'll soon see what this thing is. But the expression for this, by using above equations as well, I can write down this thing as partial mu in terms of the Levi-Civita connections, right? I can write this down as this thing, mu nu minus partial nu beta mu alpha plus this Christoffel symbol beta mu rho times again the Christoffel symbol rho nu alpha minus beta nu rho times rho, and here we'll have mu alpha, right? And so this expression is in fact closely analogous to the Yang-Mills field strength tensor. And with the help of this tensor, this tensor over here, I can actually define another quantity, that is R nu alpha, which is simply this R mu. I'll sum over this index mu mu nu alpha, right? And I can further also have another quantity that would be simply R, and it would be, if I multiply this with the metric G, let's take G nu alpha times R nu alpha, right? So you would sum over all the indices and you will get a quantity that's called R, and this R is actually your scalar curvature, if you know from general relativity. And this expression is in fact invariant under your GCT, general coordinate transformations. Now a question arises that which of these R's should I throw in my action for the gravity, right? So which of these should I put in this action, right? And so to answer this question, we'll start by considering the weak field approximation, which is simply that your metric tensor can be written in terms of the Minkowski flat space-time tensor and added to it with some constant, some perturbation h mu nu, right? And I'll tell you what this constant is in some time, but if we have this, then we can have schematically, we can have this the Levi-Civita connection. It is this thing, that it is approximately partial h, and the if I put this in the expression for this tensor R beta mu nu alpha, I will get well, I can also, if I put it in these, let me just write all of these. So you have nu alpha and R, and these will be something like, you'll have partial square h, where again h is this determinant of this field, and partial h, right? Okay, yeah, exactly. So now you will note that these expressions actually differ from those that we had in the Yang-Mills theory. So if you recall, from your Yang-Mills theory, you had F mu nu, which was approximately equal to this partial A, right? So you had your field A in that case, which is related to electrodynamics, right? Now, furthermore, the symmetry properties of the Yang-Mills field strength tensor, this one, and the Riemannian tensor, which is this one over here, are actually pretty different, right? And let me tell you a bit on how they're different. So this tensor R beta mu nu alpha allows us to build a curvature scalar, which is R, right? And we wrote an expression for R over here, this one. So you can clearly see how it allows you to build this scalar curvature. And if you look at this F mu nu, F mu nu is it is manifestly it is anti-symmetric, right? And if so, hence, then in the case of gravity, in a weak field limit, the scalar curvature R is dominating, right? So R is dominating, and we can then write down because this thing is true, so if R is dominating, then we can express our Einstein's or Hilbert Einstein's action with using this R. And therefore that answers our question where we ask that which of these R's should I use in this action, right, for gravity. And so we can then write down an invariant action as d4x square root of minus g, and we have minus 2 over kappa squared times r, right, where r is the scalar curvature, and this kappa is a constant in which we dissolve all these units, these constants. Even you'll see you'll have a Newton's gravitational constant in here as well. So the kappa square is equal to this thing. And with this, the full invariant action is actually the sum of this action that I just wrote, the Einstein's Hilbert action and the matter action. Now, if I vary this S, this total action with respect to g mu nu, I'll get something like, this is the delta, so I'm varying. I'll get something like this thing, which is the integral of d4x square root of minus g minus 2 over kappa square r and times something very interesting, which is r mu nu minus 1 by 2 g mu nu r, and of course if I was doing this thing g mu nu, I can bring it over here, and so what I'll have is, let me get rid of this very quickly. So what I'll have is this g mu nu would just come over here, so the g mu nu, right. And now from this, the this is just for the, if you vary this part of your action with g mu nu. Now if I vary this part of it, we have written an expression for these over somewhere over here, right? This is the matter action over here, and we know this is the Einstein's Hilbert action over here. So I'm just using those expressions and varying them with respect to the metric tensor g mu nu, right? So the matter action becomes d4x times square root of minus g times 1 by 2 t mu nu, and the change in this d mu g mu nu, right? Okay, now if I use these, I can easily get the equations of motion from this equation, which is setting this action is equal to 0, the change in action is 0, and this would then just imply that you have r mu nu minus 1 by 2 r is equal to this constant kappa squared over 4 t mu nu, and you further see that this constant is equal to, like I said over here, this thing. So if I divide this by 4, I'll get 8 pi g t mu nu. Now if you recall, or if you know, or if you have taken a course on general relativity, even if you have not, you must have seen this equation somewhere, right? This is known as the Einstein's field equation, and there is a factor of C4 over here, but we remember from my first lecture I said that I'll be using a convention where I'll set C is equal to 1, right? So yeah. So this is the Einstein's field equations, and of course it's just not one equation. There are a lot of equations hidden inside this one expression over here. Now with this, we have actually completed our construction of gravity as a gauge theory. So, yay. But we have to go a long way still. So I'll end this lecture with the summary of what we have done so far, right? Or what we have found out so far. So first of all, we started with, or we constructed general relativity by what? By gauging space-time translations, right? That was our first step, basically, right? And then what we did is we found that this SM, the matter action, gives us the source of gravitational field or of gravity, and we know that that source is actually your energy momentum tensor, right? It is given by the energy momentum tensor. And then we also saw, or we figured out, that the Einstein's Hilbert action is giving us the dynamics of the field. Wonderful. So this is what we have done so far up to this lecture, and I can finally say that we have gauged gravity, or we have found a gauge theory for gravity. So the next step, or next time, I'll give a little discussion on fermions in general relativity. How do we see fermions in general relativity?